All right. Well, it's 2 minutes after. We got a great crew participating right now, so we'll go ahead and get started. My name is Jeremy Gregory, and I'm the Executive Director of the Concrete Sustainability Hub at MIT. And we're delighted to have you join us for a public webinar talking about some of the research that we're doing at MIT. Our topic today is the Carbin app that we've been developing at MIT that allows us to take crowdsourced data and use it to try to evaluate the performance of pavements. And one of the questions that we often get is, hey, if you're using a cell phone, how accurate can it really be? And how does it compare to more standard measurements? And so we asked our expert in this area, Meshkat, to give you an overview of the ways in which we've been evaluating the effectiveness of the app and how it compares with more standard measurements. So just a reminder, everyone's on mute. If you have questions, you can, there's a Q&A box that should be in the lower right, and you can type questions into there and we will be monitoring that. And if we can answer it during his presentation, we will. And if we can't, then we will use that in the Q&A session at the end. So please, we encourage you to do that. So with that, I'll turn it over to Meshkat. Please take it away.
Thank you so much, Jeremy. Hi, everyone. I am Meshkat Botshekan, a PhD student at the MIT Concrete Sustainability Hub. Today, I'm going to present a review of Carbin app, which is but a crowdsourced approach for estimating road roughness power spectral density, or PSD. The algorithm is based on inverse analysis of measured vertical acceleration recorded by a smartphone mounted in an unknown position in a vehicle. Road roughness PSD is an informative quantity, as it could be used to infer useful road information indices commonly used by federal and highway agencies to prioritize maintenance and repair decisions. I will briefly talk about how the app's algorithm works, and I will validate the algorithm at two length scales. More precisely, we validate the method against 1, laser measured road roughness data for both inner city and highways, and 2, road roughness data for the state of California reported by the Department of Transportation. So without any further ado, let's get started. I would like to start off my presentation by focusing on why road quality matters. The United States, with more than 6.5 million kilometers, has the largest road network in the entire world. In fact, lengthwise, it is large enough to travel to the moon more than 8 times back and forth. Given the total number of vehicles, the increase in demand for travel and mobility, and the size of this road network, I guess it's not really surprising if I tell you that road transportation, with almost 25% share, has the highest contribution to greenhouse gas emission here in the US. In summary, it has significant impact on the following. 1, driving comfort, which is quite self-explanatory and simply means you feel less comfortable driving on rough roads. 2, fuel consumption. Recent life cycle assessments have shown that driving on roads can result in 10 to 15% more fuel consumption as compared to driving on smooth roads. 3, vehicle operating costs, which states that there is a higher chance of mechanical failure at vehicles' different components, such as suspension system, if you keep driving on rough roads. And last but not least, the environment. Driving on rough roads increases fuel consumption, which is consequently followed by more greenhouse gas emissions. So I think we now have a clear understanding of why it matters. With that in mind, the question here is, how is the road quality assessed? Perhaps the most common way of road quality assessment is through the Soil Roughness Index of International Roughness Index, which is far better known by its abbreviation IRI. But what is IRI? Suppose you have the longitudinal road profile. That is, let's say you know what is the elevation of the road at each point. IRI is then the accumulated suspension motion per traveled length of a reference car, the so-called golden car, traveling on the road profile at a constant speed of 80 kilometers per hour. The picture on the left side of my slide well clarifies what I mean. In this picture, C of X is the road roughness profile, and clearly the higher IRI, the rougher the road is, and based on this criterion, roads are classified. The chart you see on the right side of this slide tells you what are the IRI ranges for each road category. In the HDM4 model, IRI is linearly linked to excess fuel consumption depending on the vehicle type. The current or soon-to-be traditional approach of calculating IRI is expensive, laborious, scalable. In this approach, there needs to be a vehicle with accurate laser sensors that can record the elevation of the road. The road profile can then be used as the dynamic excitation of the golden car, which subsequently results in IRI. The proposed or hopefully soon to be current approach of IR estimation is a little bit more sophisticated in nature, but much more inexpensive and also way easier to use. This approach, as I will explain it later in my presentation, basically analyzes the vertical acceleration signal readily recordable by a smartphone. We have implemented this approach in Carbin app, which is now available for both Android and iOS. To itemize the benefits of the app, I should mention the following. Very easy to use. Carbin is an app, and everyone can download it and start measuring the road roughness. The app is now able to perform real-time analysis, meaning that once your trip is finished, you are able to see the results right after. This approach is highly crowdsourceable. If many people start measuring the quality of the road for one segment, we can easily crowdsource the data and the best representative. Finally, this approach is so inexpensive if we compare it to laser measurements, which here in the US cost something between $100 to $300 per lane mile. The important question is that how would the results of the two approaches compare to one another? To address this very question, it deems necessary to briefly talk about what happens in the background. How is the IRI calculated with the smartphone? So let's say we have a smartphone placed somewhere within the vehicle. It should be somewhere where the relative acceleration of phone with respect to the vehicle is zero. That is, the phone must be rigidly attached to the vehicle. The output of the phone is the acceleration signal, as you can see on the top left of this slide. The objective here is to relate the power spectral density, or the PSD of the acceleration signal, to the PSD of road roughness. Power spectral density is a classical signal analysis tool that gives insight into the power distribution of different wavelengths throughout the signal. To have this relation between the two PSDs, we first assume a half-car model, as you can see on the right side of this slide, to represent the vehicle. Half-car model is a pretty efficient model. In addition to heave, takes into account the pitch motion of the vehicle. Road roughness in this approach is assumed to be a stationary random process, fully characterized by its first two moments. Also, road roughness is assumed to be ergodic, implying the one single realization of the road roughness is statistically rich enough to represent the entire ensemble. With these assumptions and the half-car model in hand, we use the principles of random vibration theory to estimate, in addition to half-car property parameters that explain the road roughness PSD. These two roughness parameters, namely waviness number and unevenness index, as you can see in the plot, explain the power decay of roughness PSD. Before I move on to the next slide, I need to mention that waviness number and unevenness index are another method of roughness characterization. This method is used in pavement engineering, which is also suggested by ISO 8608. Although the nature of unevenness index and waviness number are distinct from IRI, the expected value of IRI can be related to C and W. So let's dive into the validation section. I present here validation at two scales, local scale and network scale. Local scale we refer to as section-by-section comparison of Carbin results with those of laser measurements. Network scale, on the other hand, is comparing the raw metrics in a statistical framework at a large scale. Here we study the state of California. In other words, owing to the ergodic nature of IRI distribution, we compare the crowdsourced results that we obtain from Carbin with the distribution by the CA Department of Transportation. So let's start with the local scale validation. Laser measurements of road roughness profiles were acquired by means of a commercially available service employing a state-of-the-art multifunction vehicle. The vehicle was equipped with a road surface profiler, and data collection was performed under prevailing traffic conditions in daytime and dry weather conditions. Two test tracks were investigated. Test track 1, a thorough dominating inner city component with about 25 kilometers length. And the second test track is a highway with a length of approximately 22 kilometers. You can see the laser measured profiles for the two test tracks in this right side. One point I want to call your attention to is that the elevation fluctuations of the two test tracks are substantially different. More precisely, elevation fluctuations of the inner city test track are approximately 3 times the value of a test track. From the longitudinal road profiles, we calculate the unevenness index and waviness number for both of the test tracks. You can see that in an average sense, both of the roughness indicators are smaller for test track as compared to test track 1, meaning that overall, the highway has a higher quality than the inner city thoroughfare. The experimental setup for validation comprises a probing vehicle, here a Ford Focus, with 3 smartphones or sensors placed at different locations within the vehicle, namely sensor 1, a phone holder attached to the bottom left of the front windshield, sensor 2, a cup holder in between the front seats, the sensor 3, a fixture on the floor behind the right passenger seat. The outputs of each sensor are the acceleration signal recorded at a 100 Hz frequency, and the speed obtained from vehicle's GPS coordinates recorded at 1 Hz frequency. The successful agreement between the experimental IRI obtained from laser measurement and the IRI values obtained from the proposed algorithm is well evident here in this slide. The following points deserve attention. Where the phone is placed in the only marginal impacts on the roughness matrix. The expected value of absolute relative error is about 6%. Provides strong evidence of the transferability of the proposed method because it can successfully capture the roughness matrix of different road classes. Furthermore, interestingly enough, following the Federal Highway Administration categorization of pavement quality, the comparison of the two test tracks shows that the highway used for validation falls within the good ride quality category, whereas the inner city thoroughfare exhibit poor ride quality. The global approach is the determination of energy dissipation using the fluctuation dissipation theorem of statistical physics. Energy dissipation condenses all the inferred parameters, including roughness metrics and car properties, into one single parameter. On the left side of this slide, the cumulative specific energy dissipation, which scales linearly with excess fuel consumption. The interesting points to mention in this plot are as follows. First, all of the sensors are roughly indicating the same amount of energy, which once again shows the marginal impact of phone position. Second, the slope of energy dissipation for test track 1 is almost 3 times that of test track 2. It is an interesting observation because if you look at the distribution of roughness, the ratio of is also 3. This in turn means that on an average sense, the cumulative specific energy dissipation correlates with the standard deviation of road roughness distribution. Finally, we perform a network scale validation for the state of California. On the left side, you can see the crowdsourced results we have from Carbin for 2 types of roads. First, interstate roads with almost 19,000 kilometers of data, and all roads with almost 28,000 kilometers. We compare our crowdsourced results with the distribution reported by the California Department of Transportation on the plot on the right side of the slide, which shows great match. I would like to finish my presentation by quickly recapping on what I presented. We propose an inverse framework which recognizes at its core the random vibrations of a smartphone mounted in a vehicle caused by the stochastic nature of the road roughness profile. The proposed approach estimates the power spectral density of by solving an L2 norm regularization problem with the half-car model as a representative of the vehicle. The rough obtained from this approach are in good agreement with the laser measurements of the same quantity, and the phone position has only marginal impact, and the framework is transferable to different road classes. It is possible to estimate the energy dissipated in a vehicle suspension system from the fluctuation dissipation theorem using the mean square average of the suspension motion. The approach provides an explicit means to estimate excess energy consumption induced by road roughness. A widespread implementation is expected to provide needed aggregate data for cities, counties, and states, not only for road quality assessment purposes, but also for evaluation of road roughness induced excess fuel consumption and related environmental impact at a higher scale, say network scale. And with that, that concludes my presentation. Thank you very much for your attention. I'm ready to take your questions or comments if there is any.
Great. Thank you very much, Meshkat. That was an excellent job. We do have, it looks like at least some of you have found the question and answer box, and we maybe have one coming in. The other thing that you can do is it is possible you can unmute yourself to ask the question, so that's just fine. But the first question we got, Meshkat. I was looking at the name of the other person, Meshkat. Thanks for the presentation. Are there any plans to integrate a full car model in the future?
Yes. So as you saw that we already have a very great agreement using the half-car model as our vehicle model. But for the purposes, so the next step for the app is technically we want to be able to classify the vehicle time based on the results that we obtain. As of now, we try to do that, and we have about 85% accuracy using the half. Eventually, if we want to be able to classify the vehicle, we need to kind of transition. We need to kind of move on to full car model. But as long as the roughness metrics are concerned, model cannot kind of improve the accuracy as we already have like 5% accuracy.
Great, thank you.
And we have one question from Luis in the audience, and he said his question is the data recording cell phone network signal dependent?
So the way that we record the data is technically we measure the acceleration of the phone at 100 hertz frequency, and also we speed from the GPS coordinates, which is measured every 1 second, which equals 1 hertz frequency. And then as of now, we just simultaneously send the data to our servers using the internet connection. But we have also implemented this thing pretty recently to our app that if someone doesn't have a good connection or is not connected to internet, we can just save the data into the local phone, and then we can send it over to our servers after the trip is finished. So there are two options. If you just want to see the results right after when you're done with your trip, then we should, like, the phone must be connected to internet with good connection quality. But if not, that's okay. But it just takes a little bit longer for us to kind of process the data, because the data must be sent to our servers through network.
Great. So you don't need to have the cell phone connection in order to use it. It's just at some point you'll need a connection in order to upload.
Yes, exactly.
Great. Okay. Another question was about whether the presentation will be available and it's something that can be shared. And yes, yeah. Well, basically there will be a follow-up to this with a link to the recording and a way that you can contact us in order to get the slides and that you can share. So.
One other question that was messaged to me privately, and it's kind of a two-part, is first, how would a DOT operationalize this? And then do you see this replacing high-speed IRI measurement?
Yes, so the way that DOT can use this, so as I mentioned, right now the DOTs do not have a clear picture of the IRI distribution within their district or state. But this approach is very crowdsourced. I would suggest you check out our website, which is fixmyroad.us. So this approach is very, very easier to use, and it's highly crowdsourceable, as I mentioned. So although we have this app for about a year now, we cover a lot of roads. DOTs had never had access to this many data points. The DOTs can kind of prioritize their based on these roads, because as of now, the DOTs kind of lack this type of data, and they just do the road quality checking visually. And this would help them to kind of better quantify the road rough based on the traffic load and the importance of the road. They can kind of prioritize their maintenance decisions, and eventually can save them some money and can kind of help the environment be a little bit more sustainable. And what was the second part of the
Yep, so the second question is, do you see this replacing high-speed IRI measurement? And I just want to follow up too. Another question was, is this available? Is this data available for review? And currently, it's online at a website called fixmyroad.us, and I'll be sharing that in our follow-up to the webinar. But just to repeat the question, it is: do you see replacing high-speed? Do you see this replacing high-speed IRI measurement?
Well, this is what we hope for, actually, because this method is very, very low cost, and in fact, like, everyone can start pitching in and measuring the road roughness. Whereas like most of the traditional methods of roughness characterization, they are expensive. Like they at least need some sort of a vehicle which has some sort of sensors attached to them, but pretty effective and very easy to use. So we are hoping that one day it could be like the main way of calculating or estimating IRI.
Great. And one other question is, are there turn-by-turn directions? Are those directions given by Waze, or are they in a generic format?
They are in, no, they're not given by Waze or anything. It's just the format.
And then one other question is, can the roughness impacts on, for example, fuel consumption be instantaneously transmitted to the Carbin user, or are intermediate calculations necessary to get that sort of estimate beyond a cell phone's capability?
So this is a good question. So your cell phone does not calculate anything. So all the data will be sent to our servers, and that's where all the calculations are. The amount of excess fuel consumption that you will experience as a result of driving on rough roads will also be reported to you right after when your trip is done. So the entire process of roughness estimation entails the energy dissipation too. So we kind of get the same results at the same time. We get the roughness metrics as well as the excess dissipated energy, which is an indicator of excess fuel consumption.
And then one other question is, specifically what sensors in a cell phone do you use? And then how do you output the data?
Yes, so we use the, first we use the GPS coordinates that are recorded by the by the phone, and we use the built-in accelerometer phones. So these are essentially the two sensors that we use in the cell phone. That we output the data is that the cell phone can measure the acceleration in three orthogonal coordinates, which is the local coordinates. But we project them to directions which are perpendicular to the road surface. So we have three acceleration files: latitude, longitude, and altitude, plus the speed, which is by the GPS coordinates. So this is how the data is stored.
And then what's the recommended speed range for making measurements?
So the algorithm that we have developed actually takes into account the effect of speed, meaning that it doesn't matter what your speed is, because based on our model, the excess fuel consumption non-linearly depends on the velocity of the car. So it doesn't matter what velocity you have. The only thing that is recommended to do is that we want the data to be we want the speed to be constant. If it has like some minor fluctuations, it's okay, but like very, very strong accelerations or decelerations are not recommended.
And then another question is, so why would you have you considered partnering with car manufacturers to collect this data as well?
Yes, we have. We've been actually we are on some pilot programs with some companies such as the fleet companies or the concrete companies, the companies that have access to like many vehicles and they record millions of miles of data per day. So we are on some sort of pilot programs with them, but it's some sort of a collaboration that we're still trying to figure out what are going to be the things that we need and what are going to be the things that they need, so that we can start collaborating on different things.
And then I guess on the other end there, how many people are currently using Carbin and collecting data with it?
So as of now, I feel like we have. I don't have the answer on top of my head, but I feel like we should have about more than 1,000. I mean, aside from the companies that we are trying to collaborate with, we have about 1,000 users, like individuals.
And then this looks like our final question so far, and it's, does the data collected go to all state DOTs or just those that ask for it?
I'm sorry, what was the question again?
Does the data that Carbin collects go to state DOTs or just the DOTs that ask for the data?
So the data, for now, we don't send the data to anyone special. The data is actually open access on the website. So anyone can technically use that, but we don't send the data to it.
All right, and that's it.
But to follow up on that, Meshkat, like we have worked with some municipalities in particular who are interested in piloting it. So it's actually a great opportunity for us to, investigate roads in a particular area using sort of conventional means, and then compare that with a municipality's collected data as well. So if there's anyone who's interested in that, we could definitely follow up with you and set something up. The other thing I would say is that the algorithm that's in the cell phone, kind of per the other question, right? It can be adapted to other vehicles, so it's not something that people have to manually do. And so that's another interesting discussion we can get into with folks who might be interested.
And I think one final question here is, what are the challenges faced so far with your development of the app, and then what are your next steps for Carbin?
So I would say the the biggest challenge that we are still facing is data collection, because the data collection, because right now we need to kind of figure out very, very good data recorded at 100 hertz frequency. And that sometimes can have some problems in the process of data collection. But we're trying very hard to kind of streamline that process and kind of optimize everything so that the users do not have to use a lot of data or doesn't drain the battery. But that is probably the biggest challenge that we're facing. It's all about how we collect and we send the data. And the next steps for the Carbin app is that we are trying to, as I mentioned earlier, we're trying to classify the vehicle without even asking the user. That helps us to kind of quantify the road roughness on the environment. The second one is that we are trying to kind of estimate the driving behavior from the way that people in a specific region drive. And yes, those are and also we are, of course, we are working on the roughness distributions and those things to try to kind of figure out what is the best plan to repair or maintain the network at the quality that would help the environment and also the users, the drivers.
Great. That's all the questions that you have listed there, Andrew?
Yep, those are all. I've answered all the questions that were privately sent to me. The rest of them would be in the publicly available.
Sure. Excellent. Well, we really appreciate everyone participating. And as you can see, we have a lot of opportunity to try to expand this beyond just the data that individuals have collected via Carbin. We really encourage you to download the app and start using it. And also, if you think there are decision makers who might benefit from it, we'd be glad to be put in touch with them as well. And so Andrew will be following up with, like I said, a link to the recording, and also if you're interested, ways to get in touch with us to get the slides, and also follow up about perhaps making use of the data as well. So thanks very much, everyone, and we look forward to seeing you on a future webinar.